So in this recording, we're going to discuss a couple of implementations of VLIW architectures, and we spend most time of the Intel architecture Itanium. Itanium has a little bit of everything. So first of all, it is a VLIW architecture in that it moves lots of the responsibility for finding instruction level parallelism to the compiler and expects the compiler to explicitly say which instructions can be worked on in parallel. It has most of the bells and whistles that we talked about needed for a good compiler support. So it has the advanced ALAT table. It allows load speculation. It allows dynamic. Actually, also has added support for dynamic branch prediction. So this is typically not supported if you have a truly go by the teaching of the VLIW that says you wouldn't need that kind of thing because this is supposed to be taken care of by the compiler, but the Intel people have decided that this is important. They also support multi-core, at least in the later implementations of Itanium, as well as multi-threading. So in some sense, they do all the tricks in the book, everything but the out-of-order execution. So Itanium 1 is the architecture or the implementation I'm going to talk about most on this recording. But the Itanium architectures are fairly compatible moving up and down with implementing binary compatibility. This picture here shows the instruction format for Itanium 1 that's also been carried forward in the later implementations. So an instruction, VLIW instruction that is, actually specifies 3 different instructions. So VLIW instruction is always 121 bits wide, encodes 3 instructions where each instruction is 48 bits. Then it has what's called a type field in the beginning that tells what kind of dependencies there are between these instructions as well as between this VLIW instruction and the following and predecessing instruction. So instruction bundle is what this is called, the 128 bits, and it encodes, as I said, 3 instructions with a 5-bit type template in the beginning. So this is takes away some of the disadvantage of the VLIW, since the template here, the type field, can specify if there is a dependence between this instruction and tell the hardware if they can all be fired off in parallel, or if we all can only, for example, fire off 1 and the next instruction fire off 2. That takes away the need to fill all the VLIW instructions with lots of no-ops, as we've seen in the previous example. So with this kind of instruction format, the code expansion is minimal compared with normal x86 implementations. So that's good. They removed some of the disadvantage for VLIW. They also allow you to actually issue 2 of these bundles per cycle. So if the type field can figure out that 2 of these bundles are not dependent on each other, you can actually take all the 6 instructions of the 2 bundles and fire them off in parallel. So this allows you to do a 6-way VLIW. And the latencies you have between the different types of instructions for the Itanium 1 is similar to what we looked at before. For example, from a floating point result to using that in an ALU that's 4 instructions. From an integer result to using it in an ALU is 0 cycles. So that means that they have implemented the bypassing from the output of the integer ALU, but the floating point ALU implementation requires several cycles inside the execution unit, and therefore you cannot do that kind of bypassing. They have support for moving loads above branches, as we discussed before. So they have the speculative instruction, which is executed here, but actually performs the work. But no exceptions will be taken for this instruction. Instead, we set a poison bit in the register, and later on you have to issue 1 more instruction, which is a load check, that only checks if the poison bit of the register is set. So the poison bit that indicates that there was some problem with this load operation, and that we have to take an exception, but that exception is going to be taken at this point in time. They also have the support for moving loads about stores. They have the disambiguation problem is solved, and they use the ALAT, Advanced Load Address Table, and that we also discussed. So you put in the tuple. So this is where you perform the advanced load, and that means that you will do all the work here. Then you will put in the tuple, address, register number, in the ALAT, and all the stores that follow will check the ALAT, and if the store happens to be to an address which is stored already in the ALAT, it will remove that entry from the ALAT. And then the load check that's being performed down here, all it's going to do is to make sure that the entry for this very register, R1, is still in the ALAT. If it's not, then we know it's have been removed from the ALAT, and we have to do some extraordinary thing to redo this load again, because the contents of the R1 will be stale data because the store was still the same, and we already discussed that. So what features is used to allow loads to move up past branches? What feature is used to allow loads to move up past stores, even though they may be to the same address? So that's the stuff hiding behind the pink box here. They also have support for the conditional execution that we discussed. So they have special predicate execution that is based on 1-bit registers, predicate registers. And we looked at the example before where we have an if then else statement here, where both the then and the else paths are relatively small. And we looked at the kind of x86-ish kind of code or RISC-ish kind of code that would be generated using this, where we have a branch here, 2 instructions, and another branch here. So 2 branches, we have 2 puny basic blocks, and if you use predicate execution, what you instead do is you have a register that will set the 1-bit value of 2 registers to the opposite values, 1s and 0s, and then you will simply execute all the 4 instructions of the if and the else path, but you guard them with the respective predicate register, and only if the respective predicate register has the right value is the instruction allowed to have any side effects. So this allow you, for example, to actually execute all these instructions in both parts of the branch, but also make sure in your implementation that you cannot have any side effects until you know the outcome of what value the predicate registers will get. So the neat thing here is, of course, that we completely remove any kind of branches, and this becomes a larger basic block. And thanks to that, the compiler people can now do have much more freedom with how they can move instructions around, because this is just a basic block. It's this basic block here, one basic block, which is part of the following basic block and the previous basic block. So what is the point of using predicate execution of the previous slide? So the Itanium has a large number, Itanium 1, I should say, has a large number of registers supported. So it has 128 general purpose registers, and these are 65-bit registers because they have this extra poison bit implemented. They also have 128 floating point registers that are 82 bits large, and they have also added 64 1-bit predicate registers and a bunch of different control structure registers that we'll not discuss in this course. So but the interesting thing here is that it has 128 registers, but the instruction set can only allow you to name 64 registers. So why do you waste this many registers? Well, you can expect that there is some kind of register renaming going on, because each instruction can only name 64 registers. We have twice as many registers implemented. And in some sense, there is some kind of register naming going on, but this is a register naming which is done with respect to how registers are shared between different incarnations of procedure calls. Okay, let me explain what's going on. So what I'm showing you here to the left are the 64 registers that can be named by the instruction set. So instruction set can identify source and destination registers as being one of these 64 registers. And to the right, I'm showing you the physical registers that actually are available on the machine. So when you start to execute a program, so let's say that you're executing out in main here, you divide these 64 registers into 32 global registers and 32 which are dynamic registers. So the global registers, actually for all incarnations, as you will see, the global registers always map to the lower 32 of the physical registers that are available in the machine. And for the first caller, as I said, seen by main here, the next 32 registers are the physical registers are the 32 dynamic registers. Now main makes a call to a function, or I will actually refer to this more as procedures, because that makes more sense in this context. But think about this as a call to a function. So calling a procedure, so this is not a process, this is a procedure, sort of like a function, but with slightly different properties. And this procedure that we call is known to have 10 input registers. That means that that it needs to get variables, 10 different variables passed to it whenever it's being called. So what you do then is, when you allocate the registers of the code, you make sure that those 10 registers that holds the 10 values that are going to be used as input to the procedure, those 10 registers are actually stored at the top part of the dynamic registers of main. And the same, physically, the very same registers are put at the bottom of the dynamic registers for the child procedure that's being called here. At the same time, we're going to change a pointer out in the physical register that says the procedure executing now has its dynamic registers starting at register number 54. So we sort of moved up the window of accessible registers to be the 32 global registers down here. The next registers here, the blue dynamic register we can't access anymore. The next register we actually can access from the ISA will be register 54. And the 10 registers we identify as input registers, and the remaining of the 32 nameable registers will be free to use for the procedure that we just called. So we can pass parameters between a caller and the procedure without doing any copying of registers, and we can just let the old values used by main in these registers just stay in those values, because nobody will be able to overwrite them. Now let's say that procedure A makes a call to some other procedure. Once more, we're going to try to figure out what kind of input and output registers. Actually, so these registers both work as input and output registers. So we can pass values from the caller to the callee, but also pass values from the callee and back to the caller. We're going to do the same trick here. How many registers do we need here as output and input registers? And once more, we're going to change the pointer in the physical register that tells us where the dynamic registers for the active process start right now. So that's going to point right here. That means the first 4 registers in this example will be the input-output registers, and the next remaining registers can be freely used by the procedure. So it's a nifty, smart way of passing information between different procedures, which really cuts down on the cost for procedure calls. So, of course, in the previous example, well, if you have a deep series of procedures calling procedures, you will eventually run out of physical registers. And to make that event a little smoother, there is what's called the register stack engine implemented in hardware that saves and restores the register from the register file. So when you start to get close to running out of registers, the register engine will save their values to memory and sort of rotate in new register again from the bottom that now can be used by no procedures making the call. So this will actually give an illusion, and of course this is hardware, it works in background, so it's not visible to software. So this gives an illusion of an unlimited register stack. You can just use this register allocation trick for calling and callees of procedures. And and this is not necessarily the register stack engine, but register stacks or register windows as they've been called in previous implementation. The trick of the previous slide is actually not new to Itanium. It's been used in Spark, still being used in Spark, and it was first introduced by the first RISC processor that came out of Berkeley. So here's the question: register windows. So what we've seen on the previous slide and here, as used in the Berkeley RISC and Itanium as well as Spark. What do they really do? So they effectively do some sort of register renaming. So they allow you to access more physical registers than you can name in the instruction set architecture. Even though this register renaming, of course, is very different from the one that we discussed in conjunction with out-of-order execution. So I talked about Itanium, and I often mention Itanium 1 in the implementations. Well, recently we just went online and got some updated information, not a lot of insight, but just going to dump some updated information about what the implementation of Itanium looks like now. Itanium was started as a joint project between HP and Intel, and the goal was to replace all the competing RISC-ish kind of implementations that was available from the Alpha was available then, the Spark was available, and HP had something called PA RISC, Precision Architecture RISC. So they pulled back their PA RISC and they instead started to support the Itanium together with Intel. It was a way for Intel to get into the server market, but that was many years ago, late 90s when that happened. So see where we are today with this implementation. So Intel last year released a new version of Itanium. Actually, some people refer to this as Titanium because they don't give the Itanium line of processor great hope for the future. Anyhow, a new processor was released. It's very impressive. The only thing that's not impressive with this processor is its market shares. So it's only present in the commercial space, and actually even HP last week announced that they will move some of their key commercial software, something called non-stop technology, will now be moved from Itanium. Before it was only supported on Itanium, and they move that technology as well to support x86. So that's a indicator that not HP, they may not have high hopes for this. Still, what they presented last year is very impressive. It's using 32 nanometer process technology, which was state of the art then, and it actually suggests a 12 wide VLIW architecture. So you will be able to launch 4 of these instruction bundles at the same time. So wow, this is impressive, and they will have up to 8 of these of these very wide VLIW cores on a chip. They also support multi-threading. So that means that this VLIW, 12-byte VLIW, may execute instructions coming from more than one thread to find enough instruction level parallelism. They have introduced even newer instructions to give the compiler people more freedom to explore parallelism. I don't know what these instructions may be beyond the instructions we already discussed, and they are heavily into virtualization because this is a commercial product. Huge L3 cache. They have a shared L2 cache as well, which is reasonably large, and very large first level caches. So the instruction cache is 512 kilobytes. That's more the size you would see of an L2 cache from x86 these days. And the data cache is slightly smaller. So it's impressive, but as I said, the market share of this is not large at all. Itanium had maybe 20% of the HPC market in the beginning of, I don't know, around 2003, 2004. Right now, I don't think they have a single entry on the top 500 list. So they have really left that market, and they're porting their own software technology onto x86 for the commercial customers. So what's the alternative here? So VLIW was meant to be simple hardware, but as you saw on the previous slide, it's a monster hardware. It is playing all the tricks but the out of order trick, and relying on compilers to some extent to do all the heavy lifting for you. But on the other hand, they don't completely trust compilers, so they threw in branch predictions and so on. So in some sense, Itanium is a halfway solution. And also, will instruction level parallelism, will it really scale? Does it pay off? Does it make sense to make a 12-wide issue architecture? How many cycles will you actually be able to find 12 independent instructions to launch at the same time? And if that is very rare, why design such a wide architecture? So there are other alternatives we will discuss, mostly in the multi-core part of this course. Is why not use just traditional out of order cores? You can put at least 8 of them on a chip today with the same number of transistors as you used here. Or why not use many skinny in order cores like they did in the mic? You can fit 60 of them on a die. Or Intel is coming out with a new very power lean technology, follow on to their Atom processor, which is slightly out of order, reorder buffer of 32, and very, very power lean. Does it make sense to have 60 or 120 of those on a core? Or maybe you would like to mix cores of different sizes, like what ARM has suggested. So they have something called Big Little, where they have the big core is an out of order core, A15, and the little is in order cores, typically A7 processors, and mixing those, maybe that makes sense. Or, as we will talk about very shortly, maybe you would like to leverage graphics technology. Maybe you would like to leverage the GPU. So there are lots more ways you can spend your transistors. Finally, before leaving VLIW, I also would like to at least have one slide covering a very innovative way of using VLIW that people worked on mostly late 1990s and the beginning 2000. This is a company called Transmeta. Transmeta was founded by a person called David Ditzel, very impressive person. His PhD exam, his PhD dissertation, was the dissertation that proposed the RISC processors. So that dissertation certainly has had lots of impact. He was also an architect for the very first couple of implementations of Spark processors at Sun. So he did the startup. And the idea here was to do a VLIW implementation. Dave had been interested in VLIWs long before he started this company. And he wanted to do a VLIW implementation where the goal was to run x86 applications. But he didn't want to implement x86 instructions in VLIW because he knew that that was not the ideal instruction set. They did release a couple of chipsets beginning of year 2000. And what they did was to come up with a completely independent architecture on the VLIW, not compatible by itself with x86 instructions. And then they used binary rewriting in software seamlessly to translate, take an x86 binary, and whenever you touch a new piece of code, no basic block or so of the x86, they dynamically translated those instructions into VLIW instructions using software. And they were banking on the fact that you make this translation once, so maybe you will refine it as well, similar to JITting. But the overhead of that software will be very small compared with how much faster we can run the processor. Turned out that they couldn't run this execution wasn't very fast. So it was low performance, but they targeted the company towards low power, desktop and smaller. And they released a couple of generations of chips, and they had a marginal impact on the market, but they were actually commercial processors by companies like HP and so on that used this processor. So as a whole, there was an investment over like $1 billion. That's just getting feeling for what it takes to do a serious chip, CPU chip startup these days. This was a $1 billion effort, and I think they made revenue maybe 300 million or so during their lifetime. So this was in some sense a failure, but what they tried out a very innovative technology, how to make backwards compatibility from one instruction set into a completely different architecture, the VLIW. Dave Ditzel is now with Intel, and I know that Intel Labs, there are several places at Intel Labs where they are exploring similar kind of ideas. So we have to see, maybe this kind of idea will resurface again in a couple of years, but this time from a much larger player.